All right, well, what can I say? Happy Monday, grade 9s. It's almost Easter. Just have a 4-day week this week, so yeah, we'll see how much we get done. Not too stressed, but I think we're gonna have a quiz. Let's see. I'm gonna see you on Tuesday and Thursday, so let's plan for Thursday. We'll have a little quiz on mirrors, and yeah, okay, and we'll talk more about it when I see you tomorrow. But yeah, here's the deal. We ended last week doing this little activity, okay, with curved mirrors, okay, this little gizmo activity thing. We filled in this chart together in class, and then we were looking at some of the questions. Now, I left you with this. Here's the deal. I told you not to bother doing anything with the SI in it, okay? What you're going to find here is the magnification. Okay, so I just wanted to fill this in with you. So what you're going to find is this is equal to negative di over do. Now, this in general is magnification. Okay, and we're going to write a capital M for magnification. And again, skip this part here. So the rule is that hi-ho equals negative dido. Okay, so hi over ho equals negative di over do. Now, what do these things mean? Okay, so just to refresh your memory, if you are drawing a ray diagram, okay, like let's say, for example, we go back to OneNote here for a second. I'm sorry, we are in OneNote. Let's go back to the concave mirror activity. Okay, and we drew some ray diagrams. And let's say we go back to one of these diagrams that we drew, this one here, okay? The height of the object here is ho, okay? That's the height of the object. Now, way down here in this tiny little image here, this guy's height is high, the height of the image. Here, maybe I'll use a different color. I'll use green. High is the height of the image. Now, the distance of the object to the lens is do, D-O, okay? Distance of object, or sorry, to the mirror, I should say. The distance of the image to the lens, and let me say it like this. The image is right there. So that distance there is di. And it turns out that there's a pattern, okay? So that the ratio of hi divided by ho, okay? So hi over ho is the definition of magnification. It's the ratio of the size of the image over the size of the object, okay? Hi over ho. Well, it turns out that that will equal the ratio of di over do, but with a negative sign. Negative sign means it's upside down, okay? In this case, for this particular image. So, coming back to our previous note there, working on this, okay? Now you understand what hi and ho and di and do actually represent, okay? And that is the magnification equation, okay? Now, if you look at some of these questions here, I'd like to go through them with you now. Let's take a look at number 8 here, okay? So it says a candle is placed 14 centimeters in front of a concave mirror. The image of the candle is focused on a sheet that is 21 centimeters, pardon me, okay? So here, let's circle that number. That is DO because the candle is the object, okay? How far it is from the mirror is the distance of the object from the mirror. Now, the image is formed on a sheet of paper that is 21 centimeters in front of the mirror. That is DI, that's the distance of the image to the mirror, okay? Now, what is the magnification? Well, what we just found was that the magnification in this case is negative DI over DO. So that will equal negative 21 divided by 14. Now, negative 21 over 14, just using your calculator, which I have one here. What is that? 2/3? Yeah, so it's going to be like 0.666 or something. So let's try it. 21 divided by 14, pardon me, is, oh, I'm sorry, 1.5. Yeah, of course. 1.5. Wait, did I do that right? 21 divided by 14. 1.5. Yeah, that makes sense because 7 is 0.5 of 14. All right, so here we go. Yeah, I had that wrong. I was thinking 1 over that. I was thinking 14 over 21. Okay, so here the deal is you get negative 1.5 times. In other words, this image will be larger. It'll be inverted. Okay, we use this meaning times as a factor. So it's the image is 1.5 times bigger than the object. Okay, so this object is therefore larger because it's 1.5 times bigger, and it's inverted because of the negative sign. Okay, this tells us it's inverted. And that's it. Now, in the next question, it says, what is the focal length of this mirror? Well, to do that, we'll use the mirror equation, which is 1 over dO plus 1 over di equals 1 over f. Now, this is one of the things that we arrived at last week, okay? So now I plug in the numbers. I go 1 over 14 plus 1 over 21 equals 1 over f. Now, this is not an exercise in finding common denominators. Now, we could do it, but we just don't want to bother. Just use a calculator and use the 1 over x button. So for me, I press 14, then I press 1 over x, then I press plus 21, then I press 1 over x, then I press equals. And then to get my answer in terms of what f is, I press 1 over x one more time, and I get that f equals 8.4 centimeters. Now, I left everything in centimeters, so my answer will be in centimeters. Okay, so here's another question. A candle is placed 9 centimeters in front of a concave mirror with a focal length of 6. How far from the mirror will the image be located? All right, so let's do question A down here. 1 over di plus 1 over do, the order of these two doesn't matter, equals 1 over f. So I'm solving for di. So I'm going to rearrange it. Here, you know what? I'll do it right underneath. Therefore, 1 over di. I'm going to subtract 1 over do on both sides. Okay, now that will get rid of it here. And so just a little algebra, 1 over f minus 1 over do. So I take out my calculator, 1 over di. Oops, there goes one note, just crashed on me. Let me load it again for you. Such lovely software. All right, let me fix it. 1 over di equals 1 over, the candle is 9 centimeters, so that's do. And the focal length is 6, that's f, obviously. So it's 1 over 9 plus 1 over 6, 1 over 6 minus 1 over 9. So I take out my calculator. 6, 1 over x, minus 9, 1 over x equals, I get a decimal, but I have to press 1 over x one last time, and I get di equals 18 centimeters. So now, what's my so that's 18 centimeters up here. What's the magnification? Well, it's going to be m equals negative di over do. That's equal to negative 18 over 9, which is 2 times, negative 2 times that is. So in other words, it's twice as big, it's larger, but it's inverted. That's the thing about the negative sign. All right, I'm going to let you finish that last, well here, let's read it together. So it's, pardon me, when an object is placed between the focal point and a concave mirror, SO, okay, no, this has SO in it, so never mind question 10. All right, there you go. So guys, the whole purpose of that, it's sort of a virtual lab. The whole idea was to take you through and get you to understand how curved mirrors work. So now I'm going to make a little summary here for you. the mirror equation. So the mirror equation goes like this, okay? First, the equation goes like this, 1 over di plus 1 over do, and again, the order of that doesn't matter on that side, equals 1 over f, okay? Where di is distance. It's not cooperating. Distance from that is weird. Let me try that again. Distance from mirror to, you're doing so well, object. Okay, and do equals distance from mirror to, oh sorry, got them backwards, pardon me. It's the writing that's confusing me because it's messing up my tablet. Anyway, object. Okay, so the object is O, image is I, and that's it. And F is the focal length. Okay, now by the way, this equation works for convex or concave. I'm just going to say note. So I'll put a little note down here, note. For concave, F is positive, okay? For convex, F is minus, okay? Negative. And that's something you need to remember, okay? Okay, so let's that's part of the mirror equation. The other part is this, the magnification. And the magnification goes like this. Okay, M equals HI over HO. That's the definition of magnification. It's just a ratio, okay? The height of the image divided by the height of your object. So you get a magnification factor when you do that. And that's equal to negative di, as we saw, over do. And that's it, okay? That's the magnification equation. Very good. Okay, so by the way, we can make several conclusions from this, and I'm just going, or several like additional notes. Okay, so I'm just going to put here underneath note. Okay, if di, okay, is greater than 0, it's therefore a real and inverted image. Okay, it will be real and inverted if di is less than 0. In other words, if it's a negative number, it's therefore virtual, so it's behind the mirror, that's the significance of that, and it will be upright as well. Okay. Yeah, that's basically it. So in other words, using the mirror equation, you can actually tell all 4 characteristics of the image: size, attitude, location, and type. Okay, you can tell all 4 of them, and it's no problem at all. Okay, and let me give you some examples of how this works. Here, examples. Let's make up some numbers. Let's say you have an object and you put it 35 centimeters away from a concave mirror. Okay, F equals 10 centimeters. And let's make this, it's concave. We know it's concave because F is a positive number. Okay, so you don't need me to tell you that. If F is a positive number, it's concave. Now I'm going to ask you to state all characteristics of this image, but we're not going to draw a picture. Now the first thing we're going to do is get its location. We'll do that by going di, okay, finding di. So 1 over di equals 1 over f minus 1 over do. Now I've already rearranged the equation like I did before. So let's plug the numbers in. I get 1 over 10 minus 1 over 35. Again, you take out your calculator. Okay, I take the reciprocal of 10, so 10 and 1 over x minus 35 and 1 over x equals. Then I take the reciprocal of my answer, and I get that di equals 14. Okay, so now I've found the location of my image. Remember how the 4 characteristics are SALT? L stands for location in that letter, in that acronym. But now I can do even better than that. Okay, I'm just going to say, therefore, now that I have a positive number for di, therefore image is real and inverted. So look at that. I'm almost completely done. Now, how did I know that? Because that's the rule. If notice the rules right here. If di is a positive number, which is the case we got here, then it's real and inverted. Okay? If di is a negative number, as you see here, then it's virtual and upright. So I just go by my little chart. Okay, it's real and inverted. Now, we've found its location. So it's 14 centimeters in front of the mirror. So this is in front of mirror. This is my location of my image. Now, it's real, it's inverted. So I have my location, my attitude, and my type. Real, inverted, okay, and at 14 centimeters in front of the mirror. All I need now is my size. To get the size, I do the magnification equals negative di over negative do. So now I'm going to put my numbers in. It's negative 14 divided by 35. And I'm going to get a decimal. 14 divided by 35 is 0.4. So I get negative 0.4 is my magnification factor. So it's therefore smaller. And we already got that it's inverted also. It's inverted because of the negative sign. And you see, that is very simple. That's how you do the magnification equation. And that's how you do a mirror equation problem. It's really easy. Use your calculator. No problem for grade 9s, I think. Okay. Now, let's do another one. This time with a convex mirror. Now, we've never done one of these before. Okay, so now I'm going to do the same thing. I'm going to say DO equals 35 centimeters. Okay, no problem. I'm going to say F equals negative 10 centimeters this time. So this is therefore convex. Okay, it's a convex mirror. And now I'm just going to plug in my values. Sorry, now we're going to state all the characteristics of the image again, starting with di. Oh, just to sum up the previous question, by the way, here's my 4 characteristics. SALT, remember? Size, we already got was smaller. Attitude, inverted. Location, 14 centimeters. In front. And type is real. Okay, now we're doing a second problem, and we're going to do the same thing. Okay, so again, 1 over di equals 1 over f minus 1 over do. Now this time we have to put a negative number in for f, so this is going to be 1 over negative 10 minus 1 over 35. Now I punch that in my calculator. I go 10 negative, pardon me, past my bedtime. 1 over x minus 35. 1 over x, my calculator. I get negative 12.857, but I have to take the reciprocal of that, and I get 7.78. So I get negative 7.78 centimeters. Now, because this number is negative, it's less than 0. So therefore, this image is virtual. So it's behind the mirror and upright. So it's not even upside down. Okay? And that is our first step. Now let's do the rest. Let's find the we found, here, let me fill it in. Size, attitude, location, and type. Wow, don't like teaching past my bedtime, that's for sure. All right, so let's take a look. Size, we don't know yet. Attitude is upright. We figured that out as soon as we got DI as a negative number. Location is behind the mirror because DI is a negative number. And virtual and behind the mirror go together, right? And the type, location, I should say, is 7.78 centimeters behind the mirror. Might as well be precise. Type is virtual. Now we just need the size. So to get the size, we'll use the magnification equation. It's negative DI over DO. So I get negative of a negative 7.78. divided by 35. Now here's the thing, the two negative signs cancel out, or whatever. Negative times a negative is a positive, if you want to think of it that way. So I'm going to get 7.78 divided by 35.222. So here I get positive 0.22. So this is again smaller. Magnification factor has to be bigger than 1 for it to be larger. But diverging lenses, you know, are always smaller, right? And that's it. Now I have a little worksheet for you. Hooray! Okay, and the worksheet is right here. So that's your mirror equation worksheet. Try those problems. We'll take them up when I see you on Tuesday. But just give them a try for now. And as you can see, here, let me do one with you just to show you the steps, okay? You don't have to change the units, by the way. You can leave everything in centimeters. Now it says, Bobby places a 4.5 centimeters in front of a tall centimeter. Okay, so let's look at this. This information here, that's how tall it is. That, my friends, is HI. Okay? Okay, and the distance on my son's playing Rocket League is getting very excited. And my other boys are getting annoyed with that. Anyway, a distance of 33.2 centimeters, so that is DO, distance of the object to the mirror. Now, if the mirror has a focal length, now obviously that is F, okay? Then what is the image height and image distance? Okay, so let's work out DI at first. So 1 over DI, we already know, it's 1 over F minus 1 over DO. So that's going to equal 1 over 28.2, sorry, whoops, 28.2 minus 1 over 33.2, okay? Yeah, and I'll let you work out what DI is from there, okay? So I just want to show you the steps because this is your work to try and practice and stuff. Now it says, what is the image height? Now we haven't really done one like that yet. So here we're going to use HI over HO equals negative DI over DO. We'll find DI first, so we have it. And now we have everything else here. So what you have to do is solve it for HI. So I'm going to cross multiply. I'm going to bring that up to the other side. So therefore HI will equal negative DI over DO times HO. So that will equal whatever you get. Well, I'll let you plug the numbers in, but it's whatever you get from the previous problem here where we found DI. So plug that in, divide by DO, which is given, and then times by, the light bulb, I made a mistake. I didn't label this right. This is the height of the object. Okay, not the height of the image. That's obviously the light bulb itself is the object. All right, and that's it. So that's how you do a question like that. So go ahead, give the rest a try. They're all pretty much the same thing. There's only 5 questions there, and I helped you do most of the first one. So you have 4 questions to practice. And our quiz will be like this. We'll have a question like that. We'll have array diagrams. We'll have a couple other questions maybe based on your understanding of these things, mirrors. And that's it. Okay. So that's mirrors. Now, guys, what I'd like you to do, if you get a chance, this is quite short. Pardon me, what I asked you to do today. But if you get a minute, what I'll get you to do is tomorrow, after you've done this mirror equation worksheet, you might want to take a look. And I will probably do this in class. That's why I'm saying this. There's a refraction gizmo. Okay. Now, you go to Explore Learning, use the logins. Okay, so let me show you that again. The logins are over here, gizmo logins. Just go to that page in OneNote. You can pick any username and password you like from the list to log in. And then the refraction gizmo worksheet is here. I highly suggest you print it out. Now I'm going to tell you, if you want to do this, follow the instructions here on the gizmo, please. Okay, if you're having issues with it, I'll quickly show you here before we go. But anyway, I'd like you to do just up to just up to this yellow line. Okay, so if you get a chance to do that, I mean, I'm not giving you very much homework, but it's just, you're at home, so this is something for you to do. I probably will do that in class, and that's why I'm telling you to do it. Now, if you're curious and you want to see what it looks like, here you see your list of gizmos. This time, oh, I'm sorry, first you click on the class. So let me click on the class. You don't have to click on the class because it'll log you into the class. This time you're going to pick, wait, where are you? Let me make sure I pick the right class. This time you're going to pick refraction. Okay, so you click on refraction. Hello, refraction. I guess it doesn't like me doing it with my fingers, so let me attach my keyboard. Let's see if I can launch it. All right. Okay, so here's the refraction gizmo. Take a quick look at it. You'll notice that, like, you've got this stuff here, and then here. Let me show you how it works. I'm going to play this. Oh, actually, I didn't want to see the waves. Okay, hang on. Let's reset that. Okay, so now, view light ray, where's your normal view light ray? Where are you? Okay, hang on. Okay. Here, let me try this. Okay, so it's going to show us the wave changing direction. Okay, this is this phenomenon refraction, by the way. And refraction is when light bends when it, say, enters a new medium. Now, in this case, it's starting up here in the air, let's say, and entering something like glass down here at the bottom. And notice how the light rays change direction. They also show you the waves. Let's see if I can alter the angle now. No, it doesn't let me. All right. So anyway, there you go. So here you can view refraction. I've actually loaded another one here too. This is the FET version. So let me maybe show you this, and then you can do the activity on gizmos yourself. Okay, but let's just do this. Okay. So here, this is a great example of refraction. I'm actually going to increase this so it's like glass or zircon or something like that. Here we can see that when light strikes the boundary between air, the white medium at the top, and then this purple medium at the bottom is something like glass or plexiglass or zircon or something. What happens is the light changes direction. It bends. And then it also partially reflects. So here you can see it either reflects or refracts. Okay, and that, my friends, is refraction. Light bending, changing directions as it goes from air into glass. It bends. Okay, so that's refraction. And oh, there's something else cool I can show you here. You can do it with a prism. So a prism is just a triangular glass. Well, I mean, you can do it with various shapes, but I'm going to show you with the prism. Einstein did this. We'll use white light. This is kind of cool. Turn it on. And if you look at this, when I get the light at the correct angle, let's see if I can move this around. Yeah, that's not bad there. Okay. Notice here the colors of the rainbow. Now I can actually exaggerate it if I get this right. Okay. So notice that the white light is separating into the colors of the rainbow. Now that is connected to refraction because the light is bending through the glass block, the triangular glass block. But also we're getting a phenomenon called dispersion, where the colors there, the colors of the rainbow separate out from the white light. Anyway, give the gizmo a try, okay? And you know, I get it if you're having a hard time with it, but do the best you can, and then just follow the instructions to the letter. And then tomorrow, when I see you, we're going to go through refraction in some great detail, okay? All right, guys, so that's it for now. Have a great day, and I will talk to you on Tuesday.